Philippines is a country comprised of 7,107 islands in Southeast Asia and the Western Pacific. The country is surrounded by water, the Sulu Sea, the Sulawesi Sea, the Luzon Strait, the South China Sea, and the Philippine Sea. And water pollution is the major problem in the Philippines. According to the Water Environment Partnership in Asia, the water pollution in the Philippines is mostly wastewater from the following sources: the industrial, agricultural, domestic sewage, and other sources like oil, mine, and chemical spills, and illegal dumping in or near the bodies of water. So almost everything that humans do, from growing food to manufacturing products to generating electricity, has the potential to release pollution into the environment. Regulatory agencies charged with protecting the environment identify two main categories of pollution: the point source and the non-point source of pollution. So a point source pollution is a contamination that enters the environment through any clear, specific location like smokestack, pipe, ditch, or tunnel. A point sources of water pollution include municipal sewage treatment plant discharges and the discharges from industrial plant. So the municipal sewage treatment plant point sources can contribute pollution in the form of oxygen-depleting nutrients and in the form of pathogens that can cause serious health hazards in drinking water and in swimming areas. While the industrial point sources can contribute pollution in the form of toxic chemicals and heavy metals. Non-point source pollution is the opposite of point source pollution, with the pollutants released in a wide area. As an example, picture a city street during a thunderstorm. As the rainwater flows over asphalt, it washes away drops of oil that leak from car engines, particles of tire rubber, dog waste, and trash. The runoff goes into storm sewer and ends up in a nearby river. So runoff is a major cause of non-point source pollution. Major sources of water pollution is the industrial waste, the agricultural runoff, and the home or city sewage. That is also called the domestic sewage. Oxygen-demanding material. Anything that can be oxidized in the receiving water with the consumption of dissolved molecular oxygen is termed oxygen-demanding material. This material is usually biodegradable organic matter, but also includes certain inorganic compounds. So the consumption of dissolved oxygen poses a threat to fish and the higher forms of aquatic life that must have oxygen to live. And almost all of the aquatic life has depend their lives on oxygen, nutrients. Excessive nutrients often lead to large growth of algae, which in turn become oxygen-demanding material when they die and settle to the bottom. Some major sources of nutrients are phosphorus-based detergents, fertilizers, and food processing waste. Next is the pathogenic organisms. The microorganisms found in wastewater include bacteria, viruses, and protozoa excreted by deceased person or animals. The widespread disease-causing organisms in the United States are Giardia lamblia and Cryptosporidium parvum, and these are a protozoan pathogens from both human and animal source. And now we have the suspended solids. The organic and inorganic particles that are carried by the wastewater into the receiving water are termed suspended solids. When the speed of the water is reduced by flowing into a pool or a lake, many of these particles settle to the bottom as sediment. Organic suspended solid may also exert an oxygen demand, while the inorganic suspended solids are discharged by some in the space but result mostly from soil erosion, which is particularly bad in areas of logging,
mining, and construction activity. And now we have dissolved. Although most people associate salty water with oceans and salt lakes, all water contains some salt. These salts are often measured by evaporation of a filtered water sample, and the salts and the other things that don't evaporate are called the total dissolved solids. The next source is the pharmaceuticals and the personal care products. These are a class of compounds that are applied externally or ingested by humans, pets, and other domesticated animals. They are released to the environment through a disposal of expired, unwanted, or excess medications to the sewage system by individual, pharmacists, or physicians. According to scientists, medicine and personal care products from human excretion may lead to become a water pollutant. So when an individual flushes the toilet, they probably don't think about the traces of the medicine and personal care products in their body that are winding up in the sewage treatment plants, streams, rivers, bays, and the ocean. But scientists have found that the bacteria in sewage treatment plants may be acting as a water pollutants and creating new contaminants that have not been evaluated for potential risks, which may have a big effect on the aquatic environment. In the green disrupting chemicals. So EDCs are substances in the environment, food sources, personal care products, and manufactured products that interfere with the normal function of your body's endocrine system. EDCs are chemicals or mixtures of chemicals that interfere with the way your body hormones work. Some EDCs act like hormone mimics and trick our body into thinking that they are hormones, while other EDCs block natural hormones from doing their job. So how are we exposed with this? Since EDC comes from many different sources, people are exposed in several ways, including the air we breathe, the food we eat, and the water we drink. EDCs can also enter the body through the skin. Next pollutant is the pesticides. So the major classes of pesticides are herbicides, insecticides, and fungicides. The herbicides are used to kill weeds. The most commonly used herbicides are atrazine, metolachlor, and alachlor. So the last source of pollutants we have is the heat. Although heat is not often recognized as a pollutant, those in the electric power industry are well aware of the problems of disposing of waste heat. Also, water released by many industrial processes are much hotter than the receiving waters, so that can affect the water. Next topic we're going to discuss is the water pollution in river. The objective of water quality management is simply to control the discharge of pollutants so that the water quality is not degraded to an unacceptable extent below the natural background level. The impact of pollution on a river depends both on the nature of the pollutants and the unique characteristics of the individual river. Some of the most important characteristics include the volume and speed of water flowing in the river's depth, the type of the bottom, and the surrounding vegetation. Total maximum daily load, or TMDL. Impaired waters are those that do not meet water quality standards that the states, territories, and authorized tribes have established for them. This assessment is made after assuming that point sources of pollution have installed minimum levels of pollution control technology. So the TMDL is computed on a pollutant by pollutant basis for a list of pollutants similar to the equation. Additional categories include acids and base that is measured as pH, pesticides, and mercury. So TMDL computation is defined as TMDL is equal to the summation of WLA plus the summation of LA plus MOS or MOS, where WLA is the waste load allocations, that is, portions of the TMDL assigned to existing and future point sources, while the LA is the load allocations, that is, portions of the TMDL assigned to existing and future non-point sources, while the MOS or MOS is the margin of safety. Effects of oxygen-demanding waste on rivers. The introduction of oxygen-demanding material, either organic or inorganic, into a river causes depletion of dissolved oxygen in the water. This poses a threat to fishes and other higher forms of aquatic life if the concentration of oxygen falls below a critical point. So now let us discuss what is biochemical oxygen demand, or BOD. So if the oxidation of an organic compound is carried out by microorganisms using the organic matter as a food source, the oxygen consumed is known as biochemical oxygen demand, or BOD. So the BOD test is an indirect measurement of organic matter because we actually measure only the change in dissolved oxygen concentration caused by the microorganisms as they degrade the organic matter. And only under rare circumstances will the THOD, COD, and the BOD can be equal, and the amount of oxygen required to oxidize a substance to carbon dioxide and water may be calculated by stoichiometric if the chemical composition of the substance is known. This amount of oxygen is known as the theoretical oxygen demand, or the THOD. So in contrast of the THOD, there is a chemical oxygen demand, or COD. COD is a measured quantity that does not depend on knowledge of the chemical composition of the substance in the water. In the COD test, a strong chemical oxidizing agent is mixed with a water sample and then boiled.
So here is an example for the calculation of theoretical oxygen demand. So compute the theoretical oxygen demand of 108.75 milligrams per liter of glucose. So first, we begin by writing a balanced equation for the reaction. If the reaction is not balanced, use the stoichiometric method. Next, if the equation is already balanced, compute the gram molecular weights of the reactants. So now we have 192 grams of oxygen to oxide 180 grams of glucose to CO2 and H2O. So the THOD of 108.75 milligrams per liter of glucose is multiplied by 192 grams of oxygen divided by 180 grams of glucose. That is equal to 116 milligrams per liter of oxygen.
While the ultimate BOD increases in direct proportion to the concentration of degradable organic matter, the numerical value of the rate constant is dependent on the following: the nature of the waste, the ability of the organisms in the system to utilize the waste, and the temperature. Nature of the waste. There are literally thousands of naturally occurring organic compounds, not all of which can be degraded with equal ease. Simple sugars and starches are rapidly degraded and will therefore have a very large BOD rate constant. Next is the ability of organisms to utilize waste. So any given microorganism is limited in its ability to utilize organic compounds. As a consequence, many organic compounds can be degraded and only a small group of microorganisms. And the last is the temperature. So the temperature is the most biological process speed up as the temperature increases and slow down as the temperature drops. Because of oxygen utilization is caused by metabolism of microorganisms, the rate of utilization is similarly affected by temperature. So the BOD rate constant is adjusted to the receiving water temperature using the following expressions, where T is the temperature of the interest, KT is the BOD rate constant at the temperature of interest, and the K20 is the BOD rate constant determined at 20 degrees Celsius, and the angle is the temperature coefficient. This has a value of 1.135 for temperature between 4 and 20 degrees Celsius, and 1.056 for temperature between 20 and 30 degrees Celsius. The graphical determination of BOD constants. So a variety of methods may be used to determine the constant and LO from an experimental set of BOD data. The simplest and least accurate method is to plot BOD versus time, and the rate equation is used to solve for decay. And one simple method around this is called Thomas graphical method. For laboratory measurement of biological oxygen demand, in order to have as much consistency as possible, it is important to standardize testing procedures when measuring BOD. Nitrogen oxidation. Up to this point, an unstated assumption has been that only the carbon in organic matter is oxidized. Oxygen assumption due to oxidation of carbon is called carbonaceous BOD, while that due to nitrogen oxidation is called the nitrogenous BOD. And now we have the oxygen deficit. So the DO-SAG equation has been developed using oxygen deficit rather than dissolved oxygen concentration to make it easier to solve the integral equation that results from the mathematical descriptions of the mass balance. So the oxygen deficit is the amount by which the actual dissolved oxygen concentration is less than the saturation value with respect to oxygen in the air, written as the D is equal to DOS minus the DO, where D is the oxygen deficit, the DOS is the saturation concentration of dissolved oxygen at the temperature of the river after mixing, and the DO is the actual concentration of dissolved oxygen. While in the initial deficit, the beginning of this DO-SAG curve is at the point where a waste discharges mixes with the river. The initial deficit is calculated as the difference between saturated DO and the concentration of the DO after mixing. Here is the equation, where D subscript A is the initial deficit after river and waste have mixed. Now we have the deoxygenation rate constant. So the deoxygenation rate constant differs from the BOD rate constant because there are physical and biological difference between a river and a BOD bottle. In general, BOD is exerted more rapidly in a river because of turbulent mixing, larger numbers of seed organisms, and BOD removal by organisms on the stream bed as well as by those suspended in the water. So Bosco has developed a method of estimating the deoxygenation rate constant from the BOD rate constant using characteristics of the stream. Here is the equation, where the KD or is the deoxygenation rate constant at 20 degrees Celsius, the V is the average speed of stream flow, and the K is the BOD rate constant determined in laboratory at 20 degrees Celsius, while the H is the average depth of stream, and the N, small n, is the bed activity coefficient. Note that the bed activity coefficient may vary from 0.1 for stagnant or deep water to 0.6 or more for rapid flowing streams. Reaeration. The value of the reaeration rate constant, or the KR, depends on the degree of turbulent mixing, which is related to stream velocity, and the amount of water surface exposed to the atmosphere compared to the volume of the water in the river. A narrow, deep river will have a much lower rate constant or aeration rate constant than a wide, shallow river. Estimating the reaeration rate constant. So here is the equation, where Kr is the reaeration rate constant at 20 degrees Celsius, the V is the average stream velocity, and the big letter H is the average depth. Note that the reaeration rate constant is also affected by the temperature and can be adjusted to the river temperature, but with a temperature coefficient of 1.024. Note that the factor of 3.9 includes a conversion factor to make the equation dimensionally correct. The reaeration rate constant is also affected by temperature and can be adjusted to the river temperature, but with a temperature coefficient of 1.024. And for various streams, the reaeration rate constant can range from 0.05 to greater than 18. And now we have the time travel. With the speed of the flow in the river and the distance downstream, the travel time may be estimated from the basic relationship between time, distance, and speed. To relate travel time to a physical distance downstream, one must also know the average stream velocity. And once the D has been found at any point downstream, the DO can be found from oxygen deficit equation. So critical point. The lowest point on the DO sag curve, which is called the critical point, is of major interest since it indicates the worst condition in the river. The time to the critical point can be found by differentiating Streeter-Phelps DO sag equation, setting it equal to 0, and solving for T using base E values for KR and the KD, or when KR is equals KD. So the critical deficit is then found by using the critical time in the Streeter-Phelps DO sag equation. TMDL mass loading. As noted earlier, the TMDL calculations are based on mass loading. To use the DO sag equation as presented here, the mass loading must be converted to a concentration. Following our general approach for calculating concentration from mass flow, we divide the mass flow by the flow of the water carrying the waste. So now we have the management strategy. The beginning point for water quality management in rivers using the DO sag curve is to determine the minimum DO concentration that will protect the aquatic life in the stream. This value, called the DO standard, is generally set to protect the most sensitive species that exist or could exist in the particular river. Nitrogenous BOD. So nitrogenous BOD can be incorporated into the DO sag curve by adding an additional term to Streeter-Phelps DO sag equation. Here is the equation where the Kn is the nitrogenous deoxygenation coefficient, The Ln is the ultimate nitrogenous BOD after waste and river have mixed, and the other terms are previously defined. So here are the factors affecting DO levels in rivers. The first is that classical DO sag curve assumes that there is only one point source discharge of water into the river, and in reality, this is rarely the case. Second is the multiple point source can be handled by dividing the river up into reaches with a point sources at the head of each reach. A reach is a length of river specified by the engineer on the basis of its homogeneity, that is, channel shape, bottom composition, slope, and so forth. Third is that some rivers contain large deposits of organic matter in the sediments. These can be natural deposits of leaves and dead aquatic plants, or can be sludge deposits from wastewater receiving little or no treatment. And the last one is the aquatic plants can also have a substantial effect on DO levels. Here is the effects of nutrients on water quality in rivers. Although oxygen-demanding waste are the most important river pollutants on an overall basis, nutrients can also contribute to deteriorating water quality in rivers by causing excessive plant growth. Some plant growth is desirable since plants forms the base of the food chain and thus support the animal community. However, excessive plant growth can create a number of undesirable conditions such as thick slime layers on rocks and dense growth of aquatic weeds. And now let us proceed to another topic for water pollution, which is the water pollution in lake. So oxygen-demanding waste can also be important lake pollutants, especially when the waste is discharged to a contained area such as bay. There are special classes of lakes which are most seriously affected by other pollutants such as toxic chemicals from industrial charges. And limnology is the study of lakes, stratification and turnover. Nearly all lakes in the temperate climatic zone become stratified during the summer and turn over in the fall due to changes in the water temperature that results from the annual cycle of air temperature changes. Lakes in cold climate undergo winter stratification as well. The biological zones. So lakes contain several distinct zones of biological activity, largely determined by availability of light and oxygen. And the most important biological zones are the euphotic, littoral, and benthic zones. Euphotic zone is the upper layer of water which sunlight can penetrate. In this zone, the plant occurs. And below the euphotic zone, here lies a profundal zone, and the transition between two zones is called the light compensation level. The littoral zone is the shallow water near the shore in which rooted water plants can grow. The extent of the littoral zone depends on the slope of the lake bottom and the depth of the euphotic zone, and it cannot extend deeper than the euphotic zone. While in benthic zone, the bottom sediments comprise the benthic zone. As organisms living in the overlying water die, they settle to the bottom where they are decomposed by organisms living in the benthic zone. Bacteria is always present in this zone. Lake productivity. A lake's productivity may be determined by measuring the amount of algal growth that can be supported by the available nutrients. A more productive lake usually will have a higher fish population, and the number of the most desirable fish may decline. An increased productivity generally results in reduced water quality because of undesirable changes that occur as the algal growth increases. So lakes can be classified as four. The first one is the allegotrophic lakes. Allegotrophic lakes have a low level of productivity due to a severely limited supply of nutrients to support algal growth. As a result, the water is clear enough that the bottom can be seen at considerable growth. Second one is the eutrophic lakes. So eutrophic lakes have a high productivity because of an abundant supply of algal nutrients. The algae causes the water to be highly turbid, so the euphotic zone may expand only partially into the epilimnium. And highly euphotic lakes may also have large mats of floating algae that typically impart unpleasant taste and odors to the water. The third one is the mesotrophic lakes. Mesotrophic lakes are lakes which are intermediate between oligotrophic and the eutrophic. The last one, or the fourth one, is the senescent lakes. These are very old, shallow lakes which have thick organic sediments or rooted water plants in great abundance. These lakes will eventually become marshes. And now let's proceed to eutrophication. Eutrophication is a natural process in which lakes gradually become shallower and more productive through the introduction and cycling of nutrients. Cultural eutrophication is caused when human activity speeds the processes naturally occurring by increasing the rate at which sediments and nutrients are added to the lake. Thus, lake pollution can be seen as the intensification and not of natural process. Algal growth requirements. All algae require macronutrients such as carbon, nitrogen, and phosphorus, and micronutrients such as trace elements. So carbon. Algae obtain their carbon from carbon dioxide dissolved in the water. When algae are either consumed by higher organisms or die and decompose, the organic carbon is oxidized back to the carbon dioxide, which returns either to the water, to the atmosphere, to complete the carbon cycle. Next is the nitrogen. Nitrogen in lakes is usually in the form of nitrate and comes from external sources by the way of inflowing streams or groundwater. The denitrification reduces the average time nitrogen remains in the lake system. The denitrification reaction is here. Next one is the phosphorus. Phosphorus in lakes originates from external sources and is taken up by the algae in the organic form and incorporated into organic compounds. The last one is the trace elements. The quantities of trace elements required to support algal growth are so small that most fresh waters have sufficient amounts for a substantial algal population. Limiting nutrient. Growth of a plant is dependent on the amount of foodstuff that is presented to it in minimum quantity. In algae, it means that algal growth will be limited by nutrient that is least available. If nutrient is least available in the water, then algal growth will decrease. For the control of phosphorus in lakes, so phosphorus is usually the limiting nutrient. So control of cultural eutrophication must be accomplished by reducing the input of phosphorus to the lake. Once the input is reduced, phosphorus concentration will gradually fall as phosphorus is buried in the sediment or flushed from lake. To be able to reduce phosphorus inputs, it is necessary to know the sources of phosphorus and the potential for their reduction. The last one is the acidification of lakes. Your rainwater is slightly acid, approximately 4 to 5 pH volume. Acidification of the water releases highly toxic Al3+ to the water. Most lakes are buffered by the carbonate buffer systems, and other factors that affect the susceptibility of a lake to acidification are the permeability and depth of the soil, the bedrock, the slope and the size of the watershed, and the type of vegetation. We are now in the next topic, which is the water pollution in estuaries. So an estuary is formed along the coasting where fresh water from rivers and streams flow into oceans. It is a place of transition where fresh water mixes with salt water, and estuaries are influenced by tides. Example of estuaries in the world is the Bay of Fundy, the Boston Harbor, the Chesapeake Bay, the Corpus Christi Bay, the Florida Bay, Hudson River Estuary, Mobile Bay, the Puget Sound, and the San Francisco Bay. So those are the estuaries we have. And the last topic we're going to have in water pollution is the groundwater pollution. The groundwater has a large measure of protection from contaminants that are found in surface waters because of its location. However, once groundwater becomes contaminated, its location and low rate of replacement with fresh water makes it difficult to return it to a pristine state. Two major contaminants is the uncontrolled releases of biological and chemical contaminants and the saltwater intrusion from overpumping of wells. So uncontrolled releases comes from a variety of sources. The discharge from improperly operated or located septic systems, the leaking underground storage tanks, the improper disposal of hazardous or other chemical waste, the spills from pipelines or transportation accidents, and the recharge of groundwater with contaminated surface water, and the leaking landfills, and the leaking retention ponds or lagoons. That is the uncontrolled releases from a different source. And for saltwater intrusion, the freshwater aquifers near oceans or above saline aquifers may become contaminated with salt water when water is pumped from wells that draw water that is too close to the freshwater saltwater interface. We can express this freshwater pressure at any point of the interference as this, where PF is the freshwater pressure, the H is the height of water table above sea level, Z is the distance of interface below the sea level, and the P is the density of fresh water. So when fresh groundwater is underlain by saline water, pumping a well in the fresh water will cause the interface to rise. It is shown in this figure. So this upconing is in response to the pressure reduction and the interface that results from the drawdown of the water table around the well. So the height of the upconing below the center of a well after an infinite pumping time at the freshwater well may be estimated by using the Beer-Andagan equation as modified by Esmorak and Mercado. This is the equation where z to the infinity is the rise of the cone center, and the Q is dual discharge, K is the hydraulic conductivity, and L is the depth of freshwater saltwater interface below well bottom prior to pumping. So a critical point in the relationship between the upconning and the drawdown is reached when saltwater cone height reaches approximately 0.4 liters to 0.6 liters. So when a freshwater is underlain with saline water, prediction of the upconing is important to prevent saltwater intrusion. And that was the end of this topic. Thank you for listening.
Ever since the day that you